Almost everything that we use or do in our daily lives are inside a system. We live in a family system where every member of the family has their own functions. If we want to go somewhere, we use the transportation system, where different vehicles are used for us to get to point A to point B. If we're going to work or school, we abide the rules inside the company system or the school system, where each rule is made for the company or school to work properly. And everything plays a role inside a government, where different governing laws are made for us to be a citizen of a said country, whether we like it or not. Different coexisting systems are around us, and we're interacting with them unconsciously. Even the stuff that we use in our daily lives has their own system. Our mobile devices or computers, for example, has small parts that is required for them to function, like the screen, transistors, and others. And if we look closely to ourselves, our bodies have parts that is required for us to live and breathe. But in general, what is a system? How can we say that a thing is a system? What are the things that we need to consider in order to call something a system? Welcome once again to another installment of the Quantitative Methods series, where we'll try to answer all of these questions and more with our topic for today: system theory, characterization, and classification. If you're new here, you may want to check out the first video tackling about the basics of quantitative methods. The link is in the description below. Let's kick things off with the first topic in today's discussion, the introduction to system theory.
But you gotta keep trying, boy, gotta keep trying. Yeah. Hey, I work at a coffee shop, but you know I be slinging Jesus.
According to Google's dictionary, a system is a set of interacting component parts forming a complex whole. You may think that this looks like a settings icon that you see on your phone, and you are right, but at the same time, this is a great representation on how a system works. Each gear is a component of the system, and when one of them spins, the others follow suit. A gear can be as complex as it can get, and can be considered as a system on its own, but it cannot work alone. That's why it needs other gears for it to work. These component parts are called subsystems, due to the fact that one can be called a system but may not function on their own. The subsystems may be real or abstract, and all components of a system are interrelated, meaning one subsystem helps another subsystem to run its function with another subsystem, just like the gears that I discussed a while back. The entire system's goal is to achieve a common objective. For us to consider whether something is a system, it must have the following. A system must be borderlined by its spatial and temporal boundaries. That answers the question, what is inside the system? A system is surrounded and influenced by its environment. This answers the question, what factors surround the system? A system is described by its structure and purpose, and this answers the question, what is the function of each subsystem? And the system is expressed in its functioning. This answers the question, what is the required input and expected output? To tackle this further, let's talk about system characterization. Based on the topic we discussed before, a system is characterized by the following attributes: system boundary, system components and their interactions, and environment. For this one, let's use college as an example of a system. Any university has functioning parts such as departments that sort the students and provide faculty members and staff to teach the students and maintain some aspects of the school. We also have canteens that provide food and supplies that the students and staff has to pay for. Administrator that governs the overall function of the university as an institution, and many more. Of course, each part has their own subparts like classrooms, laboratories, student clubs, and others. We'll consider students as the input, since without them, the faculty and staff have no one to manage and govern, and of course, the output should be graduates, ready to go out and work. First up is the system boundary. This is necessary to determine what are the parts of the system. This means this defines the scope and the limitation. It is the partitioning line between the system and the environment. This boundary may be crisp, where all the parts and functions inside the system are known and clear. Just like in colleges, departments and administration are clearly considered a part of the system. The boundary may also be fuzzy, where the parts and function of the system could be outside the system or not. The best example for this is the canteen inside the campus, as they may not be tied directly inside the institution, but they are inside the campus. Next up is the system components and their interactions. This is the fundamental building block of the system. These components can be static or dynamically changing with time, input, or the state of the system. Their interaction may be constrained or unconstrained, or controlled or uncontrolled. For example, the laboratories are not strictly used by a certain department. Other departments may use the facility as they needed, but faculty members are strictly abiding by the rules of the said institution. So the unconstrained there is the laboratories and the constrained is the faculty members. We also have unidirectional or multidirectional. For example, the canteens earns and continues its function by selling stuff to students and faculty members, but the departments cannot earn by selling stuff to the canteen. It's not like an RPG, you know. So on the other hand, registrars in the administrator side must have the students' grades that must be taken from the faculty members. Meanwhile, advisors of the class must have a copy of the past grade of the said students that can be taken from the registrar. So the unidirectional there is the canteen and the students and faculty members, and the multidirectional is the registrar and the advisors. So interaction strength may be 0 or there are no interactions at all, 1 or full interaction, and also in between or partial. They may be interacting or not. Next up is the environment. This is the surrounding where the system is. This represents everything that is important to understand the functioning of the system, but it is not a part of the system. The environment is the part of the world that can be ignored in the analysis except for its interaction with the system. This includes competition, people, technology, capital, raw materials, data, regulations, and opportunities. Now that we have a grasp on what are the characteristics of a system, let's go ahead and discuss the system classification.
Sabbath slinging Jesus is crap. Weed in his hood. I was 16.
Systems has 4 classifications and they can be classified on the basis of time frame, type of measurements taken, type of interactions, nature, and type of components. First up is according to time frame. Systems can be classified on the basis of time frame as discrete, continuous, and hybrid. Discrete systems are systems in which the state variable changes instantaneously at separate points in time. An example for this is the bank, specifically the line of people transactions inside the bank. The line can be longer from time to time or can be short. It mostly depends on the people. Next is continuous system, a system in which the state variable changes continuously with respect to time. For example is the flow of water over a dam. And lastly, we have hybrid system, a combination of continuous and discrete dynamic system behavior. A hybrid system has a benefit of encompassing a larger class of system within its structure, allowing more flexibility in modeling continuous and discrete dynamic phenomena. For example, traffic along a road with traffic lights. Just remember that few systems in practice are wholly discrete or wholly continuous. But since one type of change predominates for most systems, it will usually be possible to classify a system as being either discrete or continuous. The second classification is according to the complexity of the system. Systems can be classified on the basis of complexity, which is physical, conceptual, or esoteric. First up in the complexity are physical systems. They can be defined as systems whose variables can be measured with physical devices that are quantitative. such as electrical systems, mechanical systems, computer systems, hydraulic systems, thermal systems, or a combination of these systems. So the amount of memory inside our computers, the amount of electricity that flows in our appliances, the pixels of the camera we're using, they are measurable by different metrics and they are considered as physical. Next up are conceptual systems. Systems in which all the measurements are conceptual or imaginary and in qualitative form as in psychological systems, social systems, healthcare systems, and economic systems. Examples of this are policies that we follow. We know what's right or wrong, and people judges us from this metric, but it's not exact whether we follow it or not. We also have assumptions, since we have a basis on why we think someone is like that, but it is not exact. We also have ethics, theories, laws of science, and others. These are considered as conceptual systems. And third, we have esoteric systems. Systems in which the measurements are not possible with physical measuring devices. The complexity of these systems is of higher order. Some examples of this are alchemy, since there's no proof that this exists. I mean, the amount of love that we have for someone, the faith that we have for God and for our religion, zodiac signs, and a lot more are considered esoteric or cannot be measured exactly. Third is according to interactions. Classification of systems also depends upon the degree of interconnection of events from none to total. Systems will be divided into three classes according to the degree of interconnection of events. The components can be independent if the events have no effect upon one component to another. It could be cascaded if the effects of the event upon components are unilateral or in one direction. And it could be coupled if the events mutually affect each other or going back and forth. And lastly, we have according to the nature and type of components. These are mathematical concepts, so you can try to look them up on your algebra subjects, but we'll tackle them eventually. First up are static or dynamic components. So static systems do not depend on the past inputs to produce the output. This means that the equation is memoryless or will only depend on the value of the variable. Dynamic systems, on the other hand, depend on the past inputs and earlier system states. This means that the equation will rely on the past value of the variable to become a prime or derivative of the current formula. Next up is linear or non-linear components. Linear systems are systems in which inputs are the same as their outputs. These are equations that when we plot in the Cartesian plane, the lines will intersect on a single coordinate. Nonlinear systems, on the other hand, are systems in which input is not directly proportional to the output. This means that the plotted dot will be aligned in a curve just like this. Next up, we have time invariant and time variant components. Time invariant system parameters do not change with time. This means that the equation has two variables that has time with them but is negligible when computed. Time variant system parameters, on the other hand, change with time, as time is one of the variables. Next is deterministic or stochastic components. Deterministic systems will always produce the same output for the given input. This is a system with no randomness involved in the development of the future states of the system. Second of this are stochastic systems that will produce different outputs for a given input. So this is the opposite of deterministic that involves randomness. Next, we have lump parametric component or distributed parametric component. Lump parametric component or LPC is one in which the components are considered to be concentrated at a point. A good example for this is a suspension in a vehicle, as various components are lumped together to achieve the same thing, to dampen the feel of the road from the tires. If we're talking about the mathematical equation for this, it will look like this. And this is called the forced mass spring damper model. Distributed parameter, or DPC, on the other hand, are scattered equally to distribute in the system. An example for this is the distribution of force on a car when it is collided on a tree or post. Most cars are designed for safety in mind for the driver and passengers in a car. So in case of an accident, the car must dissipate the force in its body first. In mathematics, the equation is called partial differential equation. And lastly, we have continuous time and discrete time components. Continuous time components have their inputs and outputs defined over a contiguous range of time. In devices, this is mostly called analog signals. Discrete time components has its inputs and outputs defined only at discrete instants of time. In devices, this is called digital signals or a digital representation of an analog signal. You can observe these too when you're watching TV with an antenna or a TV box. If your TV has an antenna and the signal is getting weaker, the TV will produce static or white noise like this, and the voice will be unclear. On a TV box, however, when the signal is weak, the TV will be like this. It looks like the screen is producing screenshots, but the voice can be clear or already stopped at some point. And those are the topics that we have for today. I remember that I told you guys that we'll tackle data science for this episode, so sorry for the confusion. The syllabus stated that this topic comes first before that. But anyways, thank you so much for watching, and as always, I'll see you next time.